The latest image of the interstellar object 3I/Atlas, released just days ago, has quickly become a subject of intense discussion among astronomers, researchers, and space enthusiasts. Captured on November 5, 2025, by the Lowell Discovery Telescope in Arizona, the image provides a rare and valuable glimpse of an object that originated outside our solar system and is now passing through at a remarkable speed. At the moment the image was taken, 3I/Atlas was situated 138 astronomical units from the Sun, meaning it was 138 times the distance between Earth and the Sun, while simultaneously being 223 astronomical units from Earth. These distances place the object in a region where sunlight is still strong enough to illuminate potential cometary activity, but far enough that high-resolution imaging remains technically challenging. Nevertheless, the new observation successfully resolves the object as a bright, compact point of light whose apparent size matches the telescope's point spread function, indicating that the central body remains unresolved at the telescope's current limits of angular resolution. Surrounding the bright central core is a faint, diffuse glow reminiscent of an atmosphere or a weak cometary coma. This hazy envelope suggests the presence of gas escaping the surface of 3I/Atlas, even if only at a minimal rate. The observation was conducted through multiple filters, including a green filter specifically optimized for identifying the presence of diatomic carbon C2, a molecule commonly observed in the comet of natural comets. Interestingly, the faint atmosphere registered the strongest brightness in the bluest filter, which often corresponds to the scattering of smaller dust grains or gaseous components that fluoresce strongly under solar radiation. Though this glow indicates activity, the absence of a clear, extended dust tail in the image is both surprising and scientifically puzzling, especially given the expectations set by prior dynamical behavior. A comet approaching perihelion typically sheds mass rapidly as its surface heats up and volatile materials vaporize. This process normally releases both gas and dust, creating a visible tail that points away from the Sun due to the combined effects of solar radiation pressure and the solar wind. NASA's Jet Propulsion Laboratory previously reported the detection of non-gravitational acceleration acting on 3I/Atlas, a phenomenon often linked to asymmetric outgassing. When a comet vents material more strongly in one direction than another, it generates a reactive force that alters its trajectory slightly. Based on such observations and applying momentum conservation, calculations suggested that 3I/Atlas would have undergone significant mass loss during its perihelion passage, potentially exceeding 13% of its total mass. If 3I/Atlas behaved like a typical natural comet with substantial volatile content, such intense mass loss should have produced a prominent and easily detectable tail composed of dust and ionized gas, especially during its closest approach to the Sun when sublimation is at its peak. Yet, the new Lowell image does not exhibit this expected feature. Instead of a long, structured tail pointing away from the Sun, the object appears compact, nearly spherical in its brightness profile, with no visually obvious sign of a dust tail. This discrepancy raises questions about the nature, composition, and behavior of 3I/Atlas. One possibility is that the object may possess a surface or internal structure markedly different from typical solar system comets, perhaps composed of refractory materials with higher sublimation thresholds, or perhaps enveloped by dust grains so fine or dark that they do not scatter sunlight efficiently toward Earth. Another possibility is that the dust emission did occur, but the geometry of observation makes the tail difficult to detect. Indeed, the viewing geometry plays a critical role in the interpretation of cometary structures. At the time of the Lowell observation, 3I/Atlas was positioned only about 13 degrees away from the Sun in Earth sky. Observing any object near the Sun is inherently challenging due to the overwhelming brightness of the solar background. And when the object is nearly in front of the Sun from our perspective, any tail pointing away from the Sun will largely overlap with the line of sight. In such a situation, the tail may appear foreshortened, compressed into the central point-like appearance of the comet itself. Essentially, if the tail extends directly away from the Sun, and the observer is closely aligned with that direction, the usual elongated shape will visually collapse into a much smaller profile, making it difficult or impossible to distinguish from a surrounding coma. However, this geometric explanation, while plausible, is not entirely satisfying to astronomers, because a similar observational alignment occurred during previous imaging efforts. The Hubble Space Telescope, imaging 3I/Atlas, on July 21, 2025, viewed the object from a sunward direction at an angle of about 10 degrees, quite similar to the Lowell geometry. Despite this head-on perspective, Hubble detected a pronounced anti-tail extending approximately twice the length of the central object, oriented in the direction toward the sun. This is particularly notable because an anti-tail is a rare and intriguing feature, a structure that visually appears to point toward the sun rather than away from it, resulting from the complex orbital dynamics of dust grains that remain in the orbital plane while the nucleus moves out of it. The fact that Hubble detected such an elongation, even with a viewing angle not far from the sun, suggests that similar features should in principle be detectable again if they were present. The absence of such a feature in the recent image challenges our expectations and deepens the mystery. One interpretation is that 3I/Atlas may have undergone a significant change in behavior since its perihelion passage. It is possible that the nucleus exhausted much of its volatile content earlier than predicted, leaving behind a more dormant body less capable of sustaining strong gas and dust emission. Another possibility is that the non-gravitational acceleration observed previously was caused not by outgassing, but by another mechanism altogether. In the case of the earlier interstellar object Oumuamua, non-gravitational acceleration without an accompanying visible coma sparked widespread debate about possible non-natural explanations, including highly speculative ideas involving artificial origin. Although such scenarios remain far less likely than natural explanations, they illustrate how ambiguous data can lead to a wide spectrum of interpretations when established models fail to account for observational results. For now, the observational situation remains open-ended. The recent image, while intriguing, represents only a single data point taken under less than ideal viewing conditions. In the coming weeks, the angle between the Sun and 3I/Atlas in Earth's sky will increase substantially, offering observers a much clearer perspective free from extreme glare and geometric foreshortening that currently limit the detail visible in the images. As the separation grows to several tens of degrees, the orientation of any potential tail, whether directed away from the Sun or forming an anti-tail configuration, will become far more apparent. If 3I/Atlas possesses even a modest amount of residual dust or gas activity, the improved viewing angle should reveal it with far greater clarity. This period will therefore be crucial for determining whether 3I/Atlas behaves like a conventional comet that has simply become quieter post-perihelion, or whether it displays fundamentally different behavior, pointing to an unusual internal structure, unusual compositional makeup, or an unconventional interaction with solar radiation. During perihelion, the object was exposed to roughly 770 watts of solar energy per square meter, a level of irradiation intense enough to vaporize many types of ices rapidly. If significant volatile material remained at that time, it is difficult to reconcile the absence of a prominent aftermath in the form of dust and gas tails. Conversely, if 3I/Atlas is dominated by materials that do not sublimate easily, its behavior may reflect a class of interstellar objects that differ markedly from comets native to the solar system. As astronomers await new observations, discussions across the scientific community have intensified. Researchers are eager not only to interpret the current data, but also to revisit existing models of cometary physics and interstellar object behavior in light of the apparent contradictions. In parallel with these scientific exchanges, the object continues to capture the public's imagination, prompting widespread speculation, curiosity, and debate. Much like its predecessors 1I/Oumuamua and 2I/Borisov, 3I/Atlas has sparked a renewed interest in understanding what kinds of bodies travel the vast distances between star systems and how they behave when exposed to the environment of our own Sunday. With more data expected soon, this mystery, like so many in astronomy, will evolve as our observational perspective improves and the object continues its journey through the inner solar system.